warn you a little bit up front. The students are going to attack me. They won't harm my office, but they love me and they're locked here. The examples I'm going to show you in this talk are actually in Java languages, but the techniques I'm going to show you work across all languages, and I would use these on .NET projects. It's just a coincidence that the two examples I have in this talk are from the Java ecosystem. But these techniques actually work across all languages, all platforms. I'll show you a bit of an example from the Ruby on Rails space as well. So these work across all of these platforms. If you want more information about this topic, I've actually written a series at DeveloperWorks. This is a free series that you can go and read. There are 19 installments in this series on evolutionary architecture and emergent design. Don't bother writing that one down because it's awful and hideous. Write this one down instead. It's a much shorter link to get there. That's the table of contents of all of this material. And it covers what I'm talking about this morning, plus some other stuff. So what we're talking about today is a little bit about the nature of software design and tease apart the concept of architecture design in software, because it turns out when you split those two concepts, you can do some very useful things with both sides of it. I'm then going to talk about things that make emergent design hard, things that make it easier, and a bit about how do you harvest these things once you've found them, how do you take advantage of them. Sorry, but I want to start with the poetry of Donald Rumsfeld, who's a famous defense secretary in the U.S. And years ago, he very famously said, there are known unknowns. That is to say, there are things we now know we don't know, but there are also unknown unknowns. There are things we do not know that we don't know. And he didn't realize it, but he was talking about software here. Because this is the killer thing in software, are the unknown unknowns. Because the known unknowns you can kind of plan for. You can say, well, I don't really understand how geocoding works, but I know it has to be part of this project, so we'll kind of reserve some time for that and figure it out once we get there. That's a known unknown. It's the unknown unknowns that always nag you. This is what destroys your estimation and all the other problems in software, because we can't know those things. Big design up front and architectures fail because of these unknown unknowns. You cannot possibly plan for unknown unknowns because they are unknowable. And so in the agile world, what we try to do is say, well, instead of trying to figure out a way to predict the future, which is basically what you're trying to do when you're doing big design up front, rather than do that, why don't we try to build techniques that don't require us to predict the future, and build some techniques that let us do a little bit of work and check and see where we are and adjust course, and a little bit of work and check where we are and adjust course. That's the essence of what we do in the agile world, and this of course applies in the architecture and design space as well. One of the questions that we really need to address here is this one. What do we mean when we say software design? Well, fortunately, someone has already answered this question for us. In an essay written in 1992 in the C++ journal, Jack Reeves wrote an essay called What is Software Design? It's still available, and it's a well worth reading because you believe that it was written last week. It's very, very accurate still. And he does what a lot of people tentatively do, he did full on, which is let's compare traditional engineering to software engineering. You get a lot of very shallow comparisons all the time. You want to do deep comparison between traditional engineering and software engineering. And he made a couple of interesting observations, one of which is the final goal of any engineering activity is some type of documentation. Think if you're a civil engineer that's tasked with building a bridge over a river. What is your deliverable for that work? Is it the bridge over the river? No, it's the plan for the bridge over the river. And you turn that plan over to a manufacturing team who knows how to work with concrete and rebar to actually take your plan and implement it and build the bridge over the river. And this is one of the places where software and the physical world differ a lot, is that manufacturing for physical things means stamping out atoms. This is what makes refactoring really hard in the manufacturing world, because when you stamp out atoms, it's really hard to reconfigure them without doing something crazy like melting them down and re-stamping them out again. So they have to have their design exactly right up front because they don't have any leeway after they've stamped it out. But we don't live in a world with those constraints. We don't live in a world of atoms. We live in a world of bits. And bits are very easy to bend and change and modify after the fact. So for us, what is the manufacturing process? What is the part that takes our design and makes it do something in the real world? It actually starts moving physical things around the world like electrons. Manufacturing for us is compilation linking. That's what takes our source code and makes it do something in the real world, makes electrons flow through wires, and the internet works, and all that stuff. But then that sort of begs the question, what is our blueprint? What is our design document that allows us to do that? Our blueprint, our plan, is the source code. It is the complete source code, not just a part of it, but every part of this is the design. This is exactly like the blueprint that the civil engineer creates. And notice what a civil engineer does. They start with a sketch on a napkin, and then they do a pencil sketch, and then they eventually reach a full-blown technical document that has every detail on it. That's exactly what we're doing. Things like UML are our initial sketches of what we think the shape of the thing is going to look like, and then we refine until we eventually get to source code. If you change a single character in the source file, it changes what you manufacture. Therefore, this is our design document. Every part of this is the important part of our design document. So thinking of design as just diagrams or something like that is actually missing the point. But this is where the difference is really stark between traditional engineering and software engineering, because the most expensive part of traditional engineering is the stamping out atoms part. But in software, it's dirt cheap for us to change things. In fact, our manufacturing process is completely invisible to us now. You just, as soon as you finish typing, you just hit a key, and an army of elves inside your computer spring to life and manufacture your design in the latest version that you have in your source code. So it's impossibly cheap for us. It's the cheapest thing in the world for us to remanufacture our design. And so Jack Reese says, given that software designs are relatively easy to turn out and essentially free to build, an unsurprising revelation is that software designs tend to be incredibly large and complex. They are, in fact, the most complex things created by humans right now, I think, because we don't have a lot of the physical constraints that the real world has on keeping us from just building everything. And so a lot of the complexity that we see is imposed by ourselves because we have this environment where we can make changes all the time and build more and more elaborate things, because it costs us nothing to rebuild it and try it except time. And so Jack Reese finishes his essay with the observation that software may be cheap to build, but it's incredibly expensive to design, because every part of the software development process is part of design. Coding is part of design. Testing is part of design, because if your QA finds a bug, you change the source code, so you change the design. Every part of the software development process is really part of design. And that suggests if you're doing something like big front architecture design, you're wasting a lot of really valuable, precious time, because you can never predict the things, the unknown unknowns that are going to come up. And so doing all this work up front is almost always fruitless, because as soon as it hits the real world, all those go out the window and you have to start reacting tactically to what you actually discover the true nature of the problem. I want to talk for a second about this distinction between architecture and design. And I'll point you to a white paper that has my favorite definition of architecture in software. It's one by Martin Fowler. It's on his website. It's a white paper called Who Needs an Architect? It is about the role of architects on agile projects. And by way of defining that, he kind of accidentally gives several definitions of software architecture, which I like. And one of my favorite ones is the architectural elements of a piece of software are the pieces that are hard to change later. And you can think about that. Ask your software stack, individual pieces, are you going to be hard to change later? So the language you choose is going to be very hard to change later. The database that you choose, the web framework you choose is hard to change later. You can't trivially switch that out. But the way that you use that web framework is part of design. The way you use it to validation bits, the way you use it to workflow bits, that's easy to change later. You may have also noticed when I was talking about the article series that I wrote, I called it Evolutionary Architecture and Emergent Design. That's because you cannot have emergent architecture, because everything sits on top of the architecture. That has to be in place before you can build anything. And that's what this really abstract diagram is trying to capture here. The architectural elements are these gray boxes. And I can't just move and shuffle these gray boxes around without making everything unstable. Whereas the red boxes that sit on top of all this, I can very easily move those around and it doesn't make things unstable and shaky anymore. So the real trick in the Agile world, when you're thinking about this, is to try to build as small an architecture as you can. Because the other half of this definition is you want as few of those things as possible. You want as few things that are hard to change later as possible so that you can make changes later if you want to. And that's really this idea of emergent design, which are things that are easier to change later because things are not resting on top of them. Splitting these two things out like this allows you to think about architecture and design separately, and that is in fact what I'm primarily doing in this talk, is focusing more on the evolutionary design part of this than the emergent design rather than the evolutionary architecture. So let's talk a bit about emergent design. And I should probably give you a definition here. Something that is emergent, according to Webster's dictionary, is something that rises or emerges out of something that covers or conceals it and comes to light. The second definition is something that suddenly appears or rises unexpectedly and calls for prompt action or urgency. There are two definitions of emergent here, and this loosely corresponds to the two main aspects of emergent design that I'm going to talk about in this talk. And here's the first one. Let's say that at your office, at your work, you have a problem that is conceptually looks like this. It's this big jumbled mess of connections. And you sit and ponder it while you're at work, and you ponder it while you're on your way home, and you ponder it while you're puttering around your house. And when your wife is talking to you and you're supposed to be paying attention to her, you're still thinking about this problem in your head, kind of in a background thread all the time. You finally think about it long enough and figure out that really it does kind of belong together and there's some sort of hierarchy. This is this practice of finding abstractions and patterns that already live in your code. So let's talk about that for a second. Now, when I say the word patterns, it has a specific connotation to it from the design patterns world. Those are patterns with a capital P. And those are very useful things, because notice what the design patterns book is. It's basically, they've gone to all these different pieces of software and said, you know what, we found these common design elements in pretty much every piece of software we've ever seen, so we're going to pull those out and write a catalog for them and call it the design patterns book. Those are not the kind of patterns I'm talking about. Those are patterns with a capital P. I'm talking about patterns with a lowercase p, and what I'm calling idiomatic patterns. My contention is that every piece of software has idiomatic patterns in it, which are not important enough to write a book about, but are still important to you and your organization. So, for example, the way that you do authentication and authorization within your company is an idiomatic pattern within your company. Because every application you want to work the same way, and it either does or you hope it does. Nobody outside your company really cares exactly how you do that, but within your company it's a really important thing. That's what I'm talking about with these idiomatic patterns, these kind of localized important things, not globally important things. And I further subdivide these two guys into two kinds, technical and domain idiomatic patterns. And technical idiomatic patterns are things like validation, security, and transactional data. And domain idiomatic patterns are things like business rules and shared functionality that you discover from the technical realm. When used in this way, what we're really talking about here are effective abstractions. Here's something that has solved a problem within our organization, and the next time that problem comes up, we like to use the same solution because it works really well. That's this idea of finding and harvesting these idiomatic patterns. And that's the first aspect of emergent design that I'll talk about, is finding and harvesting idiomatic patterns that already exist in your code. And I'll show you some techniques for harvesting these guys. This is very applicable to existing or brownfield projects. The other aspect of emergent design is applicable to brand new projects. And that is the idea of the last responsible moment. The last responsible moment is this observation that when you have to make a technical decision, can you ask yourself the question, is it safe for me to defer this decision a little while? This is trying to attack the unknown problems, because over time you gain more and more knowledge and context of what the real nature of the problem is, not what you thought the nature of the problem was. And so if you can delay making an important decision for a little while, you actually have more knowledge to make a better informed decision than if you did it at the very beginning of the project. But of course you can't wait too long because then you're actually scrambling to catch up. So that's this concept of finding the last responsible moment to make a decision about something. And I'll talk about some techniques for doing that in just a bit. I'm going to show you some specific techniques to kind of enable emergent design, but first I want to spend just a couple minutes talking about things that make this hard, because that's actually more common in our world than things that make it easy. And the first thing I'll talk about is the nature of complexity in software projects. Software projects have two kinds of complexity. They have essential complexity, which is just the complexity inherent in the problem. Every problem has a certain amount of complexity that is just the nature of that problem. But unfortunately, in the software world, we also have lots and lots of accidental complexity, which are really innovative ways we've figured out how to make things more complex. And I think that's where the true innovation is happening in the software world, is figuring out how to make things ridiculously complex. If you look at the way you do most of the things in your world, if you looked at it objectively as if you just showed up, you'd go, this is crazy what we're doing here. But that's just the way it's kind of grown up over time. That's accidental complexity. And part of learning design is learning to distinguish between accidental versus essential complexity, because accidental complexity is in your way. It's making it hard for you to harvest anything because it's just in your way and hard to get away from. This is not a new distinction, by the way. This distinction originally appeared in 1975 in the book Mythical Man Month by Fred Brooks. So this is not a new concept. Second thing that makes emergent design really hard is lots and lots of technical debt. This is a metaphor by Ward Cunningham that I'm sure many of you are familiar with, because it's a really good metaphor in the software world. Technical debt are the compromises that have been imposed by external forces. There are many external forces, but two very common ones. The most common is probably schedule pressure. You need to get this done, so you need to make compromises to your design to get this done more quickly. The other are things like, there's a really famous wiki out there called the C2 Anti-Patterns Wiki, the letter C and the number 2 Anti-Patterns Wiki. And one of those entries on that wiki is the boat anchor anti-pattern. The boat anchor anti-pattern says you have to use this framework or this tool in every single project, whether it makes sense to or not, because we paid a lot of money for this tool or this framework or whatever it is. That's the boat anchor anti-pattern. You're forced to use this whether it makes sense to use it or not. That happens a lot, and that's a driver for technical debt as well, because you don't need this and you don't want it, but it's being put in there. My colleague Martin Fowler actually split technical debt into 4 quadrants as to how you end up getting there. And he calls this reckless, imprudent, and deliberate and inadvertent category. It's the we don't have time for design. This is the classic, you guys get busy, I'll go upstairs and see what they want. Prudent and deliberate is we have to ship now and deal with the consequences. And this is where you hope you are. We're under terrible schedule pressure. Let's go ahead and get this out, and we'll come back later and fix it. I'll talk about that in a second, but that never happens. Reckless and inadvertent is what's layering. This is, it's really nice to have all your code in one giant web page so you can just kind of scroll up and down and see all the global variables about it. And then inadvertent and prudent is now we know why we should have done it. Hindsight is 20/20. In fact, this quadrant down here is interesting because one of the suggestions in Fred Brooks' Mythical Man Month, if you want a really great piece of software, write it one time and then throw that one away and write it again a second time. The second one will be awesome. You know what else about the second one? You can estimate it to the day of how long you think it's going to take. But why is that? It's because the second time through, there are no unknown unknowns. You've already chased them all away. You know exactly what they are. So the second time through, it's easy to build that piece of software. But now that begs the question, if you've already got a version of it, why are you building a second version of it? So nobody ever builds it, the full thing a second time, but that would be the way to get a really great piece of software, because you chased away all the unknown unknowns, and you know exactly what you need. Technical debt is a reality. And in fact, is not necessarily an evil thing by itself. Just like credit card debt is not an evil thing by itself. When does credit card debt become evil? It's when you max it out and just make minimum payments. And that's what we have to do in the technical debt world as well. We don't need to avoid technical debt. We need to figure out better ways to negotiate repayment. So here's the world that I'd like to live in. When your project manager comes to you and says, we need to add these new features, you can say, nope, I'm sorry, you breached your credit limit on technical debt. If you'd like to speak to one of our representatives, maybe we can get you a temporary extension on credit on your technical debt. But if you keep abusing this privilege and never paying us back, we're going to declare technical debt bankruptcy on you and never listen to you again. Wouldn't that be awesome to live in that world? But we don't. But this is the problem. People incur debt and they never pay it back. And that's bad in the financial world and in the technology world. So how do you negotiate repayment? Well, first you've got to convince someone that technical debt exists before you can start a conversation about repayment. And it's one thing to go to your boss and say, you know, I'm feeling kind of sick inside and I'm kind of dreading coming to work. I'm afraid our code might be starting to suck. And they're going to say, well, can you prove that? Well, that's what you need to do is prove it. And in fact, this is one of my mantras in the agile engineering world, that demonstration trumps discussion. You can talk about this stuff until you're blue in the face. When you start showing people objective facts, that makes your case. So I want to show you a way to illustrate technical debt. Before I do that, though, I need to take a minor digression and talk about a very well-known metric in the software world called cyclomatic complexity. This has been with us for many, many years. This actually started in the C world. This works with pretty much any structured language out there. Cyclomatic complexity gives you a numeric value for the complexity of a method or a function. Thomas McKay created this formula. This is the formula. Edges minus nodes plus 2, where nodes are lines of code and edges are possible paths through that code. So for example, if you look at this little method that determines the max of two numbers, this is the edges and nodes view where I've sketched out the edges and nodes. Now I can count them up and apply the formula. So 4 minus 4 plus 2, so the cyclomatic complexity of this guy is 2. But it's kind of boring when the numbers cancel each other out like that. So here's a slightly more complex method. I draw it out in this kind of edges and nodes view and count them up, and it looks like the cyclomatic complexity of this guy is 3. 8 minus 7 plus 2 is 3. So that's the numeric value of the cyclomatic complexity of this guy, of this particular method. So armed with this metric, we can now determine the sum of the cyclomatic complexity of all the methods in the code base. And if we take that and divide it by the number of lines in the code base, we get cyclomatic complexity per line of code, which is what this graph shows. This is a graph from a real ThoughtWorks project. This is a public-facing media site in the UK. And this is from April 1st, 2006 to August 18th, 2007. The red line here is cyclomatic complexity per line of code, and the gray boxes are releases of this software. Just by looking at this graph, can you tell me what the first public go-live release of this code was? There are two common guesses. Correct answer is number 3. Because you can see here the volatility of the code base. This is schedule pressure in action. Because until they get this live, they're not making any money and they're super paranoid about it. So they're pushing the developers really hard. And the way that manifests in your code base is code that's more complex than it should be, but more to the point, all this churn and complexity where we add a bunch of complex code and refactor it away and add some, and so there's a lot of churn here. So they hit that milestone and shipped. And Eric Dernenberg, the tech lead on this project, took that part of the graph to the manager and said, okay, we see a disturbing trend here. Very often in the software world, metric trends are more important than raw numbers. And the disturbing trend is our cyclomatic complexity per line of code is getting higher and higher. So what? What's the side effect of that? Well, the side effect of that, if that keeps going up, that means that every single thing you do takes a little bit longer for every developer. Because having too much accidental complexity there means literally stuff that shouldn't be there that you're having to work around to add new stuff. And so over time, the damaging effect of this is that everything gets slower for every single person if this keeps going out of control. And so he convinced them 3.0 and 3.1 were maintenance releases, mostly refactoring away some of the technical debt they had accrued, and the inertia from that effort carried all the way down through to release number 7. Now it started creeping up again in a much more controlled way there because they changed the project structure. They actually added a second parallel development team and started kind of leapfrogging each other in features. And that drove up the complexity a little bit because now they're having to integrate two code bases together in a way that they weren't having to do before. But notice there's much less volatility here now. It's a much more common, much more even curve. And notice that you now have some interesting facts at your disposal. Because if you take cyclomatic complexity per line of code, this has a dollar value for your company. If you take the salary of all the developers divided by this, you can find out exactly how much each cyclomatic complexity point is costing you. And now you can start asking questions like, is it worthwhile having the second team because that's driving our complexity up? Is that making it more expensive than if we just had one team and had a much flatter kind of complexity curve? So now you can start playing some more objective what-if games about staffing and reasoning about is the effort that we're putting into this worth the return that we're getting on that investment. This is a great example of demonstration trumping discussion. Now, the way that Eric produced this was very much by hand, but it didn't take him much effort. He basically just found a command line tool that produces cyclomatic complexity. There are a bunch of those out there. And then wrote a little script that said, check out the first version of the code base, run the tool on it, save the results. Check out the second version, run the tool on it, save the results. He has all these results, now he mashes those all into one comma-separated values file, sucks that into Excel, and says, graph that for me. And that's exactly how to produce this graph. There are also commercial tools that will produce similar graphs for you. But this is a really nice way to demonstrate real facts. Now, you have to be careful with metrics because while we would love to have some absolutely deadly metrics in the software world that tell us absolute things, we have very few of those. This is such a young science that the best we can do with metrics now is just get kind of glimpses of a dimension of a problem. So many times you actually have to put several metrics together to build kind of a complete picture of something, and it's a little bit more art than science now, but we're making progress along those lines. So I've been talking about things that make it hard. Let me talk about things that make it easier. And one of those is testing as a design tool. So most of the time, when you hear the letters TDD, it's talking about a test-driven development. But I think it also means test-driven design, because if you do TDD properly and get out of its way, it will actually lead you to a better design. Because the design will emerge from tests, you'll get better, more tuned abstractions, and less accidental complexity. But you know, one of the things that I just said is that demonstration trumps discussion, and this sounds like a perfectly fine discussion, but I want to demonstrate this to you. So what I did was take a small problem and implement it two ways. The first way I implemented it was test after. So I just wrote the code and then I wrote unit tests for it. And then I derived it test driven, where I wrote the test first and then wrote the code. Well, let's look at the difference between those. So the problem I was solving is this kind of math trivia problem of trying to determine a perfect number. This is something that they've been doing for over 1,000 years. It's kind of numerology trivia. A perfect number is a number where the sum of the factors equals the number. So the factors are the pairs that would multiply together equal the number. So if you have 6, for example, its factors are 1, 2, and 3. And if you add 1 plus 2 plus 3, it equals 6. 28 is also a perfect number. So if you look at the factors of 28 and add them up, they'll equal 28. So that's the definition of a perfect number. That's what I want to write some code to find. So this is some Java code that goes and finds perfect numbers for me. I create a list of factors. I add 1 in the number because those are always automatically factored. And now for 2 up to the number, if number mod I equals 0, this is the same operator in C#, that is the integer division operator. If I goes to a number with 0 remainders, that means it's one of its factors. So I can add it to the list, then I'll sum them all up, and then decide if it's perfect or not. So I write this code, I write tests for it, it works. But it's really slow, like crazy slow. So I wonder if there's a way that I can make this faster, and there's a really obvious way to make this faster, right around that area right there. Because I can make an observation here that factors always come in pairs. So if my target number is 16, when I grab 2, I can also grab 8. because they always come in pairs. Which means I don't have to loop all the way up to the number. I could just loop up as high as half the number and harvest them in pairs, and that'd be a lot more efficient. I can do way better than that, though. What's even way better than that? Square root. Because the square root is, by definition, the number times itself, which equals the target number. So if I just go up to the square root and harvest them in pairs, then it'll be much more efficient. And that's exactly what I do. I go up to the square root and then harvest them in pairs. But when I do this, I get a broken test. Turns out there's an edge case here for whole number square roots. Think about 16 again. When I add 4, I'm going to end up adding 4 again. It's going to end up on my list twice. Well, that's easy enough to fix. I'll just go in and add a guard condition that said, well, if I have a whole number square root, if I don't have a whole number square root, then add the symmetrical factor. And now this works, and it's acceptably fast, and I'm calling it done. But that's the test after version. The test-driven version, I'm not going to talk about method by method. You actually understand how this works. And there's actually a bit more code here. This is actually a slightly more general solution than the other. But this is actually very characteristic of TDD code bases, in that it's lots of very small methods that usually one thing each toward the goal of making the testable. An interesting thing happened along the way of building the TDD version of this code. It was this observation. Are the factors of a number a list of numbers? Does the order matter when I'm summing these guys up? Actually, it doesn't. Factors is not a list. It's a set of numbers. And I realized that because of a broken unit test. As I was doing my TDD, I was expecting 1, 2, 3, and 6, but I got 1, 6, 2, and 3. And it made me realize that this is a set of numbers, it's not a list of numbers. But now let's go back to my whole number square root thing. Does this actually have anything to do with whole number square roots? It doesn't. It has to do with I picked the wrong data structure when I started the problem, because I chose a list instead of a set. This happens all the time. You make these little assumptions along the way, and you don't really vet them until you've already got a pile of code around them. When I encountered this problem in my test after version, what I should have done was go back and rethink all of my decisions all the way back to the beginning of time and see if that's where the problem lied. But I didn't, because I could see an easy solution. So what happened was, because I chose the wrong data structure, I created accidental complexity. And how did I fix that accidental complexity? By adding more accidental complexity. That is frequently the way people solve accidental complexity, is adding even more, obfuscating the real problem even more than they originally did. In the TDD world, I never encountered this problem. Because by the time I got to this optimization, I'd already switched everything over to sets. Because one of my little tests showed me that order doesn't matter, and so this little problem never manifested itself, and I ended up with a much better solution to this problem with less accidental complexity in it. This is what I mean when I say that testing can guide your design if you get out of its way, because it forces you to vet your assumptions at the most atomic level, which is the method level, to make sure all the assumptions you've made and the structures you've made make sense independently before you put them into the big structure, which is your overall. So TDD is an important design skill, and of course this is probably more applicable to greenfield projects, particularly if you don't have a lot of tests already, although that's not to say that you can't take a brownfield project and start adding tests as you add more functionality. Well, let's look at something from a brownfield project. And refactoring toward design. Now, this is a big pile of Java code, and actually what it does is not important. What it does is take things from a shopping cart and put it into an order of line items using low-level JDBC data connectivity. And I'd really like to see if there's some reusable design elements in there, but I can't because this is just a big, ugly pile of code. So what I need to do first is refactor this to get it down to some sort of reasonable understanding of what this code actually does. So I'm going to make a couple of refactoring passes on this. And the way I'm going to do this is based on an observation. So if you look at this code, get connection, create statement, auto commit, all this stuff, all three of those lines are really kind of joined together. from a conceptual standpoint, they're all about database connectivity. So I'm just going to take that and extract method using my refactoring tool. I'll end up here. Now, this is a side effect of using a tool for refactoring when you have lots of local variables. Because your refactoring tool has a very specific contract with you that says, when I'm finished, your code will still work exactly the way it did before. So your refactoring tool can't make decisions like, oh, I need to promote this from a local variable to a class level variable, because that has all sorts of implications about scoping and thread safety and all that stuff. So the only thing you can do is pass these guys as parameters. So I end up with a slew of parameters being passed around. But I know exactly what's going on here, and I'm an intelligent developer. I know that it's safe to move these things up to a shared class level. And so I'm going to make another refactoring pass, move those things up, and do a little bit of cleanup on these guys, and get it to here. Now we're getting somewhere, because now I can understand exactly what this code does. It sets up the infrastructure, adds orders and line items, completes. If something goes wrong, it rolls it back and finally cleans stuff up. Now I can understand what it does. And the motivation for this style of refactoring actually comes from kind of an unexpected place. The book Small Talk Best Practice Patterns by Kent Beck. It's kind of surprising because you wouldn't think a small talk book would be all that relevant in 2013 to Java, .NET, and Ruby developers. But you got to remember, these are the first guys to do object-oriented programming at an industrial scale. And they have some really interesting observations about the way things work. And this is actually an example of something that Kent Beck calls the composed method pattern. The idea of composed method is that every public method reads like an outline of what it does. And each outline element is a private method that actually does some work for you. So the goal is to get all your top-level public methods to be really nice outline. I do this, I do this, I do this, and then handle the details underneath. And notice all the modern IDEs now make it very easy to browse that code, because you just hold down the control key, the method name becomes a hyperlink, and you can browse your code literally in a code browser, kind of like the way the small talk project. And notice what I have here is if I knock out these two very specific lines of code, I can actually reuse this as kind of a template for data access. And I'm actually going to harvest it as that in just a minute. But I'm still on this subject of harvesting patterns, and so I want to show you one more refactoring exercise to go harvest some idiomatic patterns out of an existing code base. But I need one more metric for this. So we have cyclomatic complexity, which is the complexity of methods. Now I need afferent coupling. This is one of two coupling metrics in the world, efferent and afferent coupling. I care about afferent coupling in this case, which are the number of incoming connections to a class. So if I have a class and 6 other classes reference it either through an import or using or a direct namespace, then the afferent coupling of that class is set to be 6. Notice that in some ways, afferent coupling is a measure of importance, because a lot of incoming connections means you're really important to this code base. So now we have a measure of importance and we have a measure of complexity. Let's go find complicated important stuff. That's exactly what I'm going to do. So what I wanted to do to illustrate this was take an existing open source project that's been around for a really long time and see if I can find some unharvested idiomatic patterns lurking around in that code base. Now I have some criteria in mind. I want it to be a widely used code base. I want it to be around for a long time. And very mature. So I picked the very well-known web-friendly Java world struts. It's been around for more than a decade. It's in its second major release. There are literally thousands of web applications written using this framework. The source is readily available, so people can recreate this experiment. So I downloaded the struts code base, and I ran my metrics tool on it to produce cyclomatic complexity and afferent coupling numbers. Here are the results. Now, the way the particular metrics tool I ran on it produces cyclomatic complexity, this tool only reports things at the class level, which is pretty common in object-oriented languages. And so what they do is take the sum of all the methods in the class and report that as the weighted cyclomatic complexity. That's what this weighted method complexity number is. It looks like the champion in struts is this class called a double list UID, which has a sum cyclomatic complexity of its methods of 66. So if I were all about going and killing the most complicated things, this is the one I would go after. But look across the road. The afferent coupling on this class is only 3, which means only 3 other classes use this. So if I make heroic efforts to make this less complex, it only directly benefits 3 other classes. Now, it may indirectly benefit a bunch of them, but I want to change the sort order on this and sort these by importance instead. The most important class in all of structs is component. Not surprising, it's a component-based web framework. But I'm not looking for the most important. What I'm actually looking for are high combinations of numbers. And the one that catches my eye right away is this UI being guide, which has complexity of 53 and afferent coupling of 22. This is an important complex class. Let's go see what's making it so complicated. And it turns out it's primarily this method. My favorite part by far of this method is called evaluate params. The very last line of this method is evaluate extra params. So it's kind of like the developer just got tired of typing. So evaluate extra params. This is what's making this class so ridiculously complex. And so what this code does, Structs is a web-based framework, and when you send extra URI parameters, it either processes them as a form field or it passes them through and lets you do filtering and other stuff. So that's evaluate params and evaluate extra params. And I started poking around in the structs code base, and a whole bunch of the important complex classes had one of these methods in it. So I got curious, just how much of this exists in structs? So I did a little bit of command line judo. I said, given the root of structs, find me all the Java source files, and then within those, find me every one of them that has a method signature that looks like that. Here they are. Every one of these has an evaluate params and or an evaluate extra params in it. I have found an idiomatic pattern in structs. And this is a great example of these kind of idiomatic patterns because when they started building structs 15 years ago, there's no way that they said, you know what, in 15 years, the most complicated code in the entire framework will be the code that handles URL parameters. That's crazy. There's no way that could be the most complicated code 15 years in, and yet it is. What they've done is because this problem is so simple, they've re-implemented it over and over and over and over again. So, you know, I mentioned that Developer Works article series. I wrote this up as part of that series, and I was contacted by one of the structs committers who had actually independently discovered the exact same problem in that code base. And he did exactly what you should do to fix this, which is to extract that as an embedded framework. So if you download structs now, you'll notice all the parameter handling code is in a little internal framework. And by doing that, he eliminated thousands of lines of code and a couple of hundred cyclomatic complexity points. Just by refactoring that piece, that common piece out of all those classes that had gone unnoticed for more than a decade of heavy, heavy use of this framework. So in a lot of ways, metrics give you a different lens on code and let you see things that kind of fall through the cracks otherwise. So that's all examples of going and finding these things. Once you found them, what do you do with them? Because in many ways, these are the most important things in your organization. These are effective ways you solve common problems. You want to be able to reuse these things. The easiest way to reuse them is just build an API out of them. Create your own namespace for your company and build your own APIs. And that's exactly what I was in the process of doing with this little idiomatic unit of work pattern I had before. So let's solve this problem. And the way that you solve this problem to make this more generic is to apply a gang of 4 design pattern. This is a classic implementation of the command design pattern. So I can do that in Java, create my class up here that takes a command, execute that command as part of my template, and now down here this becomes, and this is kind of ugly and cumbersome in Java because of the whole anonymous interclass thing. Java doesn't quite yet have higher order functions. In fact, I'll show you a slightly better version of this and a little more C-sharpish in just a second. In fact, this is what this code would actually look like in a more modern language. Groovy is a modern dialect of Java, and this is what it would look like in C#. In Groovy, everything in curly braces is a code block, and I pass that as a parameter and can execute that as a parameter. That's exactly what that code would end up being. And now all I need to do is create one of these order guys, build my little chunk of reusable code, and pass that as a parameter. So that's one way, and that's the easiest way to harvest these things. You just build your own company-specific namespace and have all these utilities in there. Another way that is not always applicable, but is really good if you could do this, is to use, they're called annotations in the Java world, attributes in the C# and .NET world. And here's the idea. I'm not going to focus much on the implementation because it's implementation specific to Java, but notice that you can actually create attributes or annotations on classes, particularly for things like validations and other very domain-specific things. And the nice thing about these guys is they stick out because they don't look like regular code. That's exactly what you want. You don't want them to look like regular code. You want them to kind of stick out because they're unique things that you created. So this is a little validator class in Java that goes through and checks each method on a class to see if it has this annotation type, and then it calls validator if it does. The point of this is that both in Java and .NET, these guys have a lot of power because they can actually do things like look at the values of collection classes at runtime and determine things. So this is actually an annotation that says make sure that this guy is unique, that the country within my region is unique. So you can have a lot of power within these. Of course, these are not applicable for every situation because obviously everything won't fit as an annotation or attribute. But this is really nice because these do really stand out and look different from all the code around them. And that's nice because you want your really obvious patterns to stand out. So when you think about it this way, annotations or attributes are giving you an extra dimension of expressiveness in the language. You should take advantage of that extra dimension of expressiveness, particularly for things that work well for that style of use. But I want to digress for just a second and talk about a similar mechanism in the language Ruby. And this actually works on Iron Ruby and JRuby as well. So consider this whole problem. This is a unit test in the Ruby world. And let's say that this complex calculation is really time intensive. So time intensive, in fact, that when I'm running my unit test, I don't want this test to run because it takes too long. But when I'm running my acceptance test, I do want it to run because it's an important verification mechanism. So how can I set this so that it won't only run one together? Well, in the Rails world, an environment variable gets set depending on which environment you're building at a certain time. And Ruby has a very, very flexible syntax. So one of the things you can do is actually conditionally define a method to say if the build environment variable equals acceptance, then define this method. So this is syntactically more flexible than most languages, because most languages won't let you wrap ifs around methods, but Ruby will let you do that. But that's kind of ugly, because if I have several of these that I want to knock out, I have to have this if statement wrapped around methods, and it looks kind of funny. It'd be way better if I created an attribute for this. That's what I do. It's called acceptance only. This is the entire implementation for that attribute in the Ruby world. This uses a feature in the Ruby language called hook methods. These are methods that are attached to classes. And one of those hook methods is method added, which means I just add a method to the class. So I create this acceptance only method up here. This is a private variable in Ruby. That's what the @ sign means. So this is going to be true or false depending on the value of that environment variable. And so down here in method added, every time I add a method to this class, it's going to call this code. And it says here, unless that acceptance build thing is true, then remove this method. So as soon as you try to add the method, this thing's going to fire. And if that's not true, it's going to suck it back out. So it's not there if acceptance test is not true. And then it flips this flag back around to false, so that you have to put this on top of every method that you want to knock out when you do acceptance test. Let me show you a slightly different example. Let's say that we were to log everything that happened within a particular method. Here's a way to do that with a method add hook. So I come in, I grab the log method, change its name, and then define a brand new method named whatever that name was. Call the original method. What is this called from a computer science standpoint? Anybody recognize this pattern? This is aspect-oriented programming. This is called a before point cut in AOP terms, but I'm doing a bunch of stuff and I'm calling the original method. So in the Java world, this is aspect-oriented programming. In the .NET world, too, this is aspect-oriented programming. Does anybody know what this is called in the Ruby world? This is called monkey patching in the Ruby world. It's the exact same mechanism, slightly different attitude about the formality around this. The reason it's called monkey patching, by the way, is they want to call it guerrilla patching, as in guerrilla warfare. People misheard it as gorilla, like the primate. So they thought it'd be funny to call it monkey patching. That's exactly what they're calling it. They actually call this something different in the Python world. You know, dynamically typed languages are said to be duck typed because it quacks like a duck, it must be a duck. So this is alternatively called duck punching, of going around and making it say something that it wouldn't normally say, like punching it in the face. This is a really powerful mechanism. Notice that in the Ruby world, you don't have to have a separate framework that weaves your bytecode and changes your source. It's actually built directly into the language. That's really powerful because expressiveness matters a lot. This is an example from an old example. This is how you harvest things from a form in structs, and this is how you do it in Ruby on Rails. Expressiveness in programming languages matters much more so than many people think. Because if code is designed, and I agree with Jack Rees on this, you want the most expressive medium you can find. And a lot of times this manifests as metaprogramming. And so if you're in, for example, a C# environment, that's a very powerful language that has really nice metaprogramming facilities. Make sure you understand how to use those. Because that is your design palette. In some ways, that is your little pouch of drafting tools. The features of your languages become your design vocabulary because those are the building blocks for the design you're going to create. And you want the most expressive design you could possibly get, so you want to use the richest tools you possibly can. This also gets into abstraction styles. Everyone here is intimately familiar with the imperative abstraction style, which encompasses both structured and modular programming and object-oriented programming. But you also hear a lot about functional programming these days. In fact, I'm doing 2 functional programming talks at this conference, one called Functional Thinking and one on Closure. This is a different abstraction style. This is a different set of tools to apply to problems. And so normally when you think about switching abstraction styles, you think, well, I have to switch languages to do that. But that's actually not true anymore. Because in languages like C#, there are lots and lots of functional programming constructs. So for example, in C#, you should really never iterate anymore. You should map and filter and reduce and use some of those functional concepts for higher level abstractions. But even without going that far, you can get different abstraction styles, even on top of really familiar abstractions. A great example of that is the concept of an anti-object. This comes from a paper that was delivered at UPSLA in 2006 called Collaborative Diffusion. And their observation in this paper was that the metaphor of objects can go too far by making us try to create objects too much inspired by the real world. If all you have is a hammer, every problem looks like a nail. If the only abstraction your language supports is object orientation, you try to cram every problem into object orientation. An anti-object is a kind of object that appears to do the opposite of what we think it should be doing. So here's an example. It's kind of like this. Is this a vase or is it 2 faces? It depends on your perspective. So here's the classic anti-object example. And it's how the video game Pac-Man works. Now, I have to warn you, I'm about to explain to you how Pac-Man works, so the next time you play Pac-Man, it's not going to be nearly as fun. So if you want to leave now, I understand. Sometimes knowledge comes at a price. This is a pretty high price, but it's pretty good knowledge, so it may be worth the trade-off. Think about the original Pac-Man console game that came out in the very... That's not what they did. They took an anti-object approach. Instead of building intelligence into the characters, they built the intelligence into the maze. The maze is basically a big giant state machine that for every turn, it runs some rules on each one of these cells. And they invented this concept of Pac-Man smell. Now when Pac-Man is sitting on a cell, it has maximum Pac-Man smell, and the cell he just vacated has maximum Pac-Man smell -1, and it decays really fast, and all the ghosts do is wander around looking for Pac-Man smell, and they move a little bit faster than Pac-Man, and that's the whole game. Pac-Man smell. So, the next time you play Pac-Man, you can actually run right up on one of the ghosts because they can't see you coming, they can only tell where you've been. They only turn into you by accident because they can't see where you've been or where you're coming, they can only tell where you've been. And see, they put a really subtle trick in the game. The ghosts have eyes but no nose. They should have had a nose and no eyes. then it would have been a much easier game to solve because then you'd know that you can run right up to them, but they fooled you by putting eyes on them. This is a classic example of we have too many constraints to solve the problem we think we should solve, but can we flip the problem on its head and solve the background problem? It turns out that's a much easier solution. We've actually done this in a couple of our projects. We had a train leasing project, and we had to figure out how to sort cars on rail yards, and we ended up building intelligent tracks rather than intelligent cars, because the track was really the thing that needed to react, not the cars, to be able to sort them to get them in the right place. So these are all kind of examples of finding and harvesting idiomatic patterns. In the couple minutes I got left, I want to go back to this concept of last responsible moment and give you some tools. So I can't tell you exactly when the last responsible moment happens. This is the hard part of doing this kind of engineering. But I can give you some clues as to how to find it. So when you look at a part of your project, a component or a framework piece of whatever it is, and look at the amount of complexity that it takes on over time. Anytime it upticks the amount of complexity it's taking on, that might be a good time to ask, has your last responsible moment arrived, and should I replace you with something else? So one of the big differences of being an agile architect is that there's much more direct awareness of what's going into the code all the time. Big design architects, most of their work is done up front, and then they move on to the next big design up front. Whereas here, you have to have a much more intimate relationship with code, because your code and your design and your architecture are shifting all the time. And that's exactly what you want, but you need to make sure that you can guide it in the correct direction. One of the really useful techniques here that we use a lot in the Agile world is the concept of spike. This is a time box experimental coding exercise. So let's say that you've been asked to add geocoding to your application, and you don't know what geocoding is, you're not even sure you can spell it, and someone's asking you to estimate that. One of the great anti-patterns in the C2 anti-patterns wiki is the give me estimates now anti-pattern. That says that no matter how many qualifications and waffle words you put in front of that estimate, as soon as numbers come out of your mouth, you've entered into an ironclad contract that you'll risk your life to make this come true. And so it's not worthwhile saying, well, this is a crazy guess and all this stuff, because the numbers, when they come out, become the ironclad contract. That's where spikes come in. Spikes are time box experimental coding exercises to see how much knowledge I can gather on this so that I can make a more informed guess as to what the effort's going to be. This is chasing away some of the unknownness from the unknown unknown. That's how you manage those things on an ongoing basis in the project, is try to just in time learn what you can about the problem. So to summarize, evolutionary architecture and emergent design are made much easier by good engineering practices. So obviously the refactoring techniques I showed you really rely on good unit tests and the ability to do refactoring your code base. Well-partitioned code and good components is much easier to evolve over time. That doesn't mean you can't use these techniques, but these certainly make it easier to facilitate this. Trying to predict the future very often leads to over-engineering. This is one of the biggest crimes in over-engineering on projects, because you're not paying attention to the last responsible moment. So, for example, let's say that you're on a project and you hit a need for something like a message queue. But you don't know exactly what you're going to need a message queue for, so your knee-jerk reaction is, well, let's buy the most expensive, complex one we can, and we'll grow into it over time. And that's a terrible mistake, because what you're buying is technical debt. Anything that's in a tool or framework that you're not using, but you still have to interact with, is technical debt. In a lot of cases, you buy these tools expecting to expand into them, and you never do, so you're just paying for technical debt that has no benefit. Last responsible moment is better than that, because you try to get just enough tool for now, with the realization that we may need to swap that out at some point in the future when the requirements get more robust, but we don't want to overbuy something. And this is a very subtle distinction, but a really important one. Prefer pro and reactive to predictive. What big design up front is trying to get you to do is predict what's going to happen, which is doomed to failure. Instead, be proactive. Try to look for the last responsible moment. Try to pay attention to what's going on in your code base. And during development, be reactive when things happen. Look at metrics around things. Look at the pieces of your design or architecture that you think may be subject to be swapped out now for something else. React to those things in an ongoing way. This, of course, reflects the fact that this is a much more direct relationship to code in the Agile world or the traditional world, but it does give you some really nice techniques for doing this. It looks actually like I'm out of time, and I don't want to hold this room up for the transition. I will be here for the rest of the week, so if you have any questions about this, I'll be more than happy to answer them for you. Thanks very much for coming, and I'll see you later.